Hello everyone. Today I am going to discuss a very important topic, that is crystal field theory. This topic is very much related with the transition metal complexes, that is the coordination compounds. Now if we see the transition metal complexes, most of them are having their very intense color, and these color origin of these colors, if we want to investigate, these colors are very much related with the orbitals present in the metal. So transition metals have their partially filled or empty d orbitals. Here we can see that, and we know there are 5d orbitals present. So you can see the picture of 5d orbitals. So these d orbitals are very much related with the intense color of the transition metals. We know there are the 7 colors present in this region. So you can see here the transition metals having their different transition metals having different colors in the visible region. So for example, titanium having the intense violet color, chromium having green color, manganese having light pink color. Iron in 3 plus state is yellow in color, whereas in 2 plus state it is dark green in color. Cobalt is uh, blue or bluish violet color. Nickel is green, or copper is blue in color. So most of the transition metal complexes are very much in colored compounds. And also if we see the gemstones, we know we use those gemstones as ornaments in our finger ring. Most of the gemstones are very have the very intense color. So gemstones, the if we see their content, the composition, actually they contain aluminium oxide. It is actually colorless, but when chromium is mixed with aluminium, then in actually it is the composition of ruby. Ruby is one of the very common gemstone we know. We use it. It is red in color. Whereas amethyst is another gemstone where manganese is present as one of the transition metal. In amethyst, it is actually due to presence of manganese with aluminium. It is violet in color. Topaz, another transition gemstone. Iron is present here, so it is reddish in color, reddish brown color. Sapphire is blue in color. Here the transition metal present titanium and cobalt, whereas emerald, chromium is present. It is green in color. So transition metals are present in gemstones. That's why they are colored compound. Now we are going to reveal the relation between the metal ligand orbitals and the bonding and the color of the compounds. Now you see here when one metal orbital overlaps with the ligand orbital, there is formation of bond between metal and ligand. In these cases, mostly we consider metals as the electron deficient center, that is metal orbitals are vacant, whereas ligand orbitals are filled electron rich center. So when the electrons from ligand orbitals are shared between metal and ligand, there is the bond formation between metal ligand, orbital overlapping between metal and ligand, and this type of bond is called coordinate covalent bond, that we know. So transition metal compounds mainly contain coordinate bonding between the metal and ligand, where the metals are considered as the electron deficient, ligands are considered as electron rich. Now we'll go to the inner picture of the bonding, that is how the bonds are formed in for the transition metal complexes. So we have to study, that is actually known as crystal field theory, the bonding of the transition metal complexes. So when crystal field theory was proposed, some assumptions were made. First assumption was the metal and ligands both are considered as the point charges. That means there is no overlapping of the orbitals of metal and ligand. That is very important. So as we know, this type of bonding is known as ionic bond or electrostatic bond. So in case of CFT, purely electrostatic interaction is considered between ligand and metal. And also for the when the complex is at the stable state, it is considered that there is the minimal interaction between the metal and ligands. They remain far away from each other in undisturbed condition. Now what happens? Suppose you have a free metal ion. It has its d orbitals, it has some electrons in its d orbital. You know there are 5 set of d orbitals, which are they? dxy, dyz, dzx, dx square minus y square and dz square. So you can see in the first case, that is here you see it is the 5 set of d orbitals with the of the metal ion, and all are having the similar energy, so they are called degenerate orbitals. So 5 degenerate orbitals are present for the metal ion when it is in the free state. What does it mean? That means there are no ligands in the environment of the metal. Now when the ligands approach towards the metal, then what happens? Metal is electron deficient, so obviously the electron rich center will get attracted by the metal. So the ligands will approach towards the metal. When ligands are approaching, there is interaction between ligand and metal. As a result, due to that interaction, some disturbance occurs. As a result, the orbitals get some higher energy. You can see the average energy of the orbitals increased here due to the interaction between the ligand and the metal. So you know for octahedral field there are 6 ligands surrounding the metal center. So those 6 ligands approach towards the metal, so their energy increases. Now what happens? The ligands approach more and more towards the metal center. Now there when they approach towards the metal center, here all the d orbitals do not remain oriented in the along the same direction. So if we see the 3d orbitals dxy, dyz and dzx, they remain in between the axis. If you see the picture, whereas dx square minus y square and dz square, these two orbitals remain along the axis. Very important point it is, you have to remember it is, you should remember dxy, yz and zx. Those remain in between the axis, means dxy remains in between x and y axis, dyz in between y and z, and similarly dzx in between x and z. Whereas dx square minus y square, the lobes remain along 2 lobes along x-axis, 2 lobes along y-axis, whereas dz square 2 lobes along z-axis. So for octahedral complexes, another important point is when the ligands approach, here the ligands approach along the axis, along z-axis, along y-axis and along x-axis. So when the ligands approach along the axis, so the orbitals which remain along the axis, they will face more interaction. So which orbitals will face more interaction? Dx square minus y square and dz square orbitals, they get higher in energy due to more interaction, more disturbance, so they get higher in energy, whereas the other 3 orbitals, to balance the total energy of the system, they become lower in energy. So you can see here dxy, dyz, dzx become lower in energy, whereas dx square minus y square and dz square become higher in energy. So the lower such that the total energy remains constant. So the 3d orbitals, lower 3d orbitals, this set is known as T2g set, T2g set, whereas the upper 2 orbitals, those are known as the EG set of orbitals. Now if we see the energy gap between these two, you can see the energy gap between the T2g and EG is the del O. This is the energy gap, and for the each orbital in the T2g set, the energy is minus 0.4 del O, whereas for the EG set, each orbital has energy plus 0.6 del O, such that for the total energy remains minus 1.2 del O for T2g. For EG it is plus 1.2 del O. They cancel out each other, so the total energy becomes 0. As we have considered previously, it has the 0 energy, which is called the barycenter. Barycenter means when the energy is considered as the before splitting, the energy is considered as 0. So here the 5d orbitals get splitted. It is, this phenomena is known as splitting of d orbitals, and it is actually the basic of the crystal field theory. Due to the interaction between metal and ligand, the orbitals get splitted into two sets. One is the T2G lower one, and the higher one is EG. At the gap, energy gap between T2G and EG, that is known as del O, or it is known as CFAC. It represents actually CFAC, that is crystal field stabilization energy. So more del O value, more CFAC, less del O value, less CFAC. Now next is the so for some complexes we get the lower CFSE, for some complexes we get the more CFSE. So there are few factors which actually are responsible for the extent of splitting of the d orbital. So there are actually three factors. First is the position of the central metal. If we consider the coordination compound, there is the metal, central metal, and there are the ligands surrounding it. So if the central metal ion present in the 5d orbital in periodic table for the 5d period, then for those type of complexes the CFSE will be maximum. If the metal is present in the 4d period, then it is intermediate, and if it is present in the 3d period, then it has the minimum CFSE. In case of, if we consider, if we see periodic table, nickel, suppose the group 8 element, that is the nickel, palladium, platinum. Nickel is the 3d metal, palladium is 4d metal, just below it there is platinum, that is 5d metal. So for nickel the CFSE will be minimum. If you take some nickel complex considering the same ligands, that complex has the minimum CFSE, minimum splitting, lower splitting. For the palladium complex, intermediate splitting, and for platinum complex the splitting will be maximum. Now going to the charge on central metal ion. If it has higher oxidation state, then its CFSE will be higher. Lower oxidation state, CFSE lower. For example, chromium. If we consider chromium, one is chromium 3 plus, another is chromium 2 plus. So considering the same ligands environment, chromium 3 plus has more CFSE than chromium 2 plus. So the oxidation state actually also responsible for the extent of splitting. Now the ligands are also responsible. The nature of ligand, that is also responsible for CFSE. So few ligands can interact to the less extent, and few ligands can interact to the more extent with the metal. So the ligands interact to the less extent to the metal, those are called weak field ligands. You can see in the left hand side, and ligands interact to the more extent to the metal, those are called the strong field ligands. So depending on their field strength, that is their ability to interact with the metal center, they can be given in a series in increasing order. That series is known as spectrochemical series. Few ligands are given here in this spectrochemical series. Also the other ligands also can be placed here in this series depending on the requirement. So here the mainly the common ligands which are used in transition to form the transition metal complexes, those are here given. You can see the left hand side, the iodide, bromide, chloride, fluoride, those are only actually weak field ligands. So they interact to the less extent. As a result, the splitting gap between the two d orbitals decreases. So lower, you can see here smaller splitting, that corresponds to lower CFSE, means the del O value is low. As the gap is low, the del O value becomes lower, and that corresponds to high spin complexes. Now if we go to the strong field ligands, there is more interaction, more gap, more splitting, more del O value, that corresponds to low spin complexes. So thus the nature of the ligands also can predict also is responsible for the extent of splitting of the complexes. So depending on the splitting of the d orbitals, here two types of spin states arise. One is the low spin, another is the high spin. So when the gap is small, then those are the low spin complexes. When the gap is higher, then this is high spin complexes. You can see here this blue color table here. You should remember this one. That is very important in calculation of CFSE. Now going to the next slide. Now once the orbitals get splitted, the electrons are present in the orbital, so we have to fill them by electrons. Now first, if we consider the d1 case, how many electrons are there in the d orbital? One electron. So where to place the electron? Always we have to start from lower energy orbital, then step by step we'll go to the higher energy orbital. And during the filling, as you know already, you have studied in school level, that is always the one orbital will be filled by one electron each. When all the orbitals are filled by one electron, then we have to come back again. We have to put the second electron in the orbital, and when two electrons are there in one particular orbital, then they will have their opposite spin. That we know according to the Hund's multiplicity and Pauli's exclusion principle. So here you see D1. So where to put the electron? You see that in the T2G set, the lowest set will put the one electron. D2, where to put the two electrons? In the T2G set only, one electron in first orbital, second electron in the second orbital. For the D3 case, here three electrons in the 3 orbital. Now going to the D4 case. Here the interesting situation arises, that is where to put the fourth electron. We have two options. Either we can put it in the higher energy level, or we can put the fourth electron in the lower energy level. In that case, we have to change the spin of the electron. Right? In the same orbital, two electrons will have always opposite spin. So when the which type of filling we will consider here? If the gap is larger in case of T2G and EG, if this gap is higher, the Delo value is higher, then what happens for the fourth electron? It is difficult for us to put the fourth electron on the higher level because it needs higher energy. So where to put it is easier to put the fourth electron in the lower energy level only. In that case, you can see the two electrons get paired up. So only two electrons having the same spin. So as the spin number becomes lower, so it is called low spin complex. When the Delo is higher, so it happens when the Delo value is high. High Delo value, then it occurs. Now if we go to the another situation when the Delo value is lower, the gap is smaller, when the ligand field strength is lower or the metal has lower oxidation state, then this gap is smaller. In that case, the fourth electron we can easily put to the higher energy level rather than to the lower energy level. So the this situation occurs when the gap is smaller between them. Then this configuration is known as T2G3 EG1. 3 electrons in T2G, 1 electron in EG. For the D4 low spin complex, it is T2G4. All the 4 electrons are in the T2G orbital. Now going to the D5 case, similarly for low spin, how to put them? 1, 2, 3, 1 each. Then again the fourth electron in the same orbital and fifth same orbital as the gap is higher. So it is T2G5 it becomes. And for the D5 high spin complex, as we easily can put the two electrons in the higher energy level, all the orbitals having the one electron. So it becomes T2G3, 3 electrons in the T2G level and 2 electrons in the EG level. Similarly, you can see D6. So for D6, you see the low spin all are paired up, all the electrons are paired up. For D6 high spin, what happens? How to put? First T2G set, first orbital 1 electron, second orbital 1, third 1, fourth EG set, first orbital 1, second orbital 1. Then we have 6 electrons. So the sixth electron to be placed in the T2G set with the pairing of energy. Always we have to start from lower energy. Now again the D7, similarly for the low spin complex there is one unpaired electron you can see in the higher energy level, whereas for low high spin complex there are three unpaired electrons, two in Ag level, one is T2G level. Similarly D8, D9, D10. For D10 you can see all are filled up. So in this way one by one you can fill them by electron depending on the number of electrons. Now depending on the number of electrons in the orbitals and their spin state, there will be the crystal field stabilization energy. So if we want to calculate the CFSE for first T2G1 D1 case, there is one electron in the T2G level as we have seen already. How many unpaired electron there? One unpaired electron. So what is the CFSE? CFSE will be minus 0.4 del O. So if we take CFSE can be taken in two ways. Either you can take in the form of del O, then it will be 0.4 minus 0.4 del O. Minus 0.4 del O, or you can take it as the minus 4 and plus 6. For T2G it is minus 4, for EG it is plus 6. So that is your choice, whatever you can take, go with the any of the rule. So here I am going minus 0.4 del O and it is shown here as the DQ, so anyone you can use here. Now T2G2, two electrons in the T2G level. How many electrons? Two, each having how much? 0.4 minus 0.4 del O. So 2 electrons, the value will be minus how much? Minus 0.8 del O. Minus 0.8 del O. Now again for the T2G3, the value will be minus 0.4 into 3, that is minus 1.2 del O. Now we go to the high spin case D4, that is weak field ligand high spin case. So one electron will go to the Ag level. Now the value becomes minus 0.4 into 3 plus 0.6 into 1. So it becomes how much? Minus 1.2 plus 1.6 plus 0.6, that becomes minus 0.6 del O. Minus 0.6 del O. So for D4. Similarly D5, D6 you can calculate. Similarly for the strong field ligand, that is the low spin complex, you can calculate the CFSE values. So CFSE value you can see here for the D10 complex, the CFSE value is 0. All the orbitals are filled up by electron, whereas for the D5 high spin complex, when all orbitals are symmetrically filled, all are having one electron each. So here also for D5 CFSE is 0. Thus we can calculate the CFSE. Now we are going to the next case, that is the tetrahedral complexes. So we know coordination complexes may be of octahedral shape, there may be of tetrahedral shape, also other shapes are there like square, planar, trigonal, bipyramidal. So according to the BTech syllabus, I will only discuss here the octahedral and the tetrahedral cases. Now if the case is tetrahedral, then what happens? There also splitting occurs. Tetrahedral means there will be one metal, and how many ligands are there? There will be 4 ligands, L4, and there is the one metal. So octahedral means 6 ligands, tetrahedral means 4 ligands. So here the difference between octahedral and tetrahedral is that for tetrahedral complexes the ligands approach towards metal center in between the axis, whereas for octahedral complexes ligands approach along the axis. That is the main difference, major difference between octahedral and tetrahedral complexes. Now also you can see here, when there are the no ligands, free metal state, 5d orbitals, they are degenerate having same energy. When ligands approach towards them, similarly they are having the higher energy, but they are also still they are degenerate. But when ligands approach more towards the ligand, the metal, the gap is very less between metal and ligand, then what happens? The interaction becomes stronger. As a result, few orbitals face more interaction, few orbitals face less interaction. Here, as the ligands approach in between the axes, as I already said, so the orbitals present in between the axes, metal orbitals which present in between the axes, will face more interaction. As a result, for example, which orbitals dxy, dyz, dzx, they become higher in energy, whereas dx square minus y square and dz square being oriented along the axis, they face lower interaction, so become lower in energy. So the 2d orbitals are this set is known as here the E set, and the 3d orbitals, this set is known as T2 set. Here one thing to should be remembered, that here we will not use any G sign. G stands for Girardet. Girardet is Latin word. Girardet means symmetry. Octahedral complexes are symmetrical, so we will use G sign. For tetrahedral complex, it is non-symmetrical, unsymmetrical, so we will not use any G sign. Here you see the splitting pattern becomes opposite to the octahedral. E becomes lower, T2 becomes higher, and the reason already I discussed here, due to the approach of the direction of approach of ligand, it happens. Now you see here the gap between E and T2 here is del T. For octahedral it was del O, here it is del T. And for each orbital in E level, the energy is minus 0.6 del T, minus 0.6 del T, whereas for each orbital in T2 level, the energy is plus 0.4 del T. It is plus 0.4 in E level, minus 0.6 del T. And here for tetrahedral complexes, as the extent of interaction is less here, so del T, the gap, is very less than del O. Always del T is always del O. Now how much less? That is the figure 4 by 9. So del T is 4 by 9 del O. As it is fraction, you know del T is always less than del O. So as the gap in tetrahedral complex is less, the T2 and E gap is less. So it always, tetrahedral complexes are high spin complexes. So there is no low spin tetrahedral complexes are formed. So now if we come to calculate CFSE, again we can calculate here. Now let's consider D1 case. Though there is one electron, where to put the electron? Again in the lower energy level, the filling rule is same here also. First we have to start from lower energy level, that is E1. What will be the energy? As I already said, the energy is minus 0.6 del O. How many unpaired electron? One unpaired. Now going to the D2, two e orbitals each having one electron. This is the case. So how much energy? Minus 0.6 into 2 minus 1.2. How many unpaired electrons? 2. Now D3, all are high spin, as I already mentioned. So D3, 2 electrons in E level. Now as the gap is small, third electron always will put to the higher energy level, that is the T21. So the configuration is E2 T21. So what is the CFSE? Minus 0.6 into 2 plus 0.4 into 1, so it becomes minus 0.8 del T. How many unpaired electrons? 3. In this way you can calculate all of them. For D5 always, as all are having symmetrically filled orbital, 0 CFSE, and for D10 also, D10 case the unpaired electron is 0, all are paired and all orbitals are symmetrically filled, so CFSE is 0. So you can try calculate the CFSE for all the cases. Now what is the importance of CFT? So from CFT we can say the color of the compounds. Now the question is, so from where the color generates? Here we have seen CFT actually tells the splitting of the d orbitals. Due to that splitting, some orbitals become lower in energy. Two sets are actually generated. So when suppose one electron present in the lower energy level, by supplying some energy, that electron can be promoted to the higher energy level. So when if you stop supplying the energy, excess energy, then the electron will again come back to the lower energy level, and during that time some amount of energy will be released in the form of ray, and that energy falls in the visible region, that is 400 to 800 nanometer. That's why we can see the color of the complexes. Now some complexes are blue color, some are green, some are red. Why that difference? That depends on the extent of the CFSE, that is the gap between T2 and E level. Depending on that gap, the frequency falls in the green region or red region or blue region, like this. So we can thus explain the color of the complex. And second one is to predict the magnetism. If there is the unpaired electron, then it becomes paramagnetic. If there is no unpaired electrons or electrons are paired up, then it becomes the diamagnetic complexes. So when complex is paramagnetic, that means when one electron, unpaired electron is present, it is paramagnetic. Two unpaired electron, it is also paramagnetic. But the extent of paramagnetism depends on number of unpaired electron. So the extent of paramagnetism is given by magnetic moment, that is mu. So for paramagnetic, mu is non-zero. What is the formula to calculate mu? That is root over n into n plus 2. N is the number of unpaired electron, right? And what is the unit of mu? The unit of mu is bm, that is Bohr magneton. That is the unit. So for one unpaired, suppose here you can see the table, when there is the d1, one electron in d orbital, for the high spin octahedral complexes or tetrahedral complexes, there is one unpaired electron, right? So now put the n is equal to 1, you will get the mu value after calculation 1.73, and observed value is very close, that is 1.75. In this way, for D2 there are 2 unpaired electrons, the n value is 2. For D3, 3 unpaired electrons. For D4, 4 unpaired electrons. In this way, putting the values of n like this, we can calculate the mu. So we can predict about magnetism. Whereas when it is suppose D5, you see here D5, the maximum paramagnetism observed 5 unpaired electrons, whereas for D10 you see all are paired up. So here mu is 0. So D10 case where mu is there, it is diamagnetic. So D10 state is complexes having D10 or electron, those are diamagnetic. So that is all about you. So thank you.